Hi everyone, my name is Walid Dabbous and I'm a researcher at INRIA in Sofia Antipolis. I'm sorry I can't be with you today to present the paper in person. I recorded this video to introduce our work called To RIS or Not To RIS, a ray tracing study of RIS-assisted indoor 5G communications. This study was carried out at INRIA by the Diana team members and was partly supported by the EU Converge project. Let me start by introducing Reconfigurable Intelligent Surfaces, or RIS. As you may know, these surfaces have been proposed to meet the challenges of next-generation wireless communication standards. So what exactly is a RIS? It is a surface composed of many passive, controllable elements that can manipulate how electromagnetic waves propagate. So by configuring these elements, we can modify the characteristics of the incident signal, for example, to redirect it, focus it, or suppress unwanted paths. As we'll see, RIS can be used to improve coverage, enhance spectral efficiency, or support other applications. Now, let us see how the RIS works. In this figure, you can see a base station acting as a transmitter, a receiver, and an obstacle that blocks the line of sight communication. So, without the RIS, the direct link is lost, which degrades the received signal. With the RIS, however, we introduce an additional component in the environment, the RIS itself. The RIS received the incident signal from the transmitter, controls its phase and amplitude according to the configuration of its passive element, and redirects the reflected wave towards the receiver. So depending on the technology used, these elements could act as simple reflectors or as more advanced controllable antennas. This controlled reflection allows us to focus the energy towards the desired direction, improving the received signal. So one obvious application is coverage enhancement, as shown here. But RIS can also be used to increase spectral efficiency by reducing interference and supporting multi-user beamforming, where different signals are redirected toward different users. Additionally, RIS can contribute to environment friendliness by reducing unnecessary electromagnetic emissions and lowering transmission power, since we can better control where the energy goes. So in these slides, we see different operating modes for RIS. On the left, the top figure shows the reflective mode, where the base station sends a signal and the RIS reflects it toward different users. Below, the figure shows the refractive mode, where the RIS transmits the signal through itself toward user behind it. These different modes can be very useful in various scenarios. For example, as illustrated here on the right figure, RIS panels could be deployed on building facades, ceilings, aerial vehicles, or even inside offices to enhance coverage or, in some cases, absorb signals. This last capability can be used for physical layer security, where we want to prevent signals from being intercepted by malicious users. In this work, however, we focus on the reflective mode, since our scenario is based on coverage improvement. So the main question we investigate in this paper is, can we use RIS to improve coverage and signal quality for indoor communications? To answer this question, we did a study using the Sionna ray tracing module. Sionna is an extension for radio propagation modeling built on top of Mitsuba renderer and the TensorFlow machine learning framework. So how does Sionna work? First, we need to define the environment or the scenario. We can either create a synthetic 3D model of the environment using Blender, which integrates well with Mitsuba, or we can capture the real environment using tools like LiDAR to obtain a 3D scan, which we then process in Blender. Once the scenario is ready, we specify the characteristics of the transmitters and receivers, including their location, orientation, and antenna parameters. After that, we run the ray tracing computation, which calculates all possible propagation paths within the environment and estimates the received signal strength at different points. So, with this tool, we can either model a real chamber, like the anechoic chamber at INRIA, by scanning it with LiDAR, or we can manually define a synthetic 3D model. In both cases, the resulting environment is fed into Sionna, where we introduce the RIS model and study its impact on coverage. Sionna produces results such as coverage maps and receive signal strength maps, which allow us to analyze the RIS performance. So in our experiments, we considered a simple synthetic indoor scenario, a rectangular room, first without obstacles and then with an obstacle. In the line of sight scenario at the left, we placed an isotropic transmitter and a receiver, along with a single RIS mounted on a wall. The RIS consisted of 12 modules, each containing 256 reflective elements. We defined the transmission power and antenna characteristics, and then we analyzed the received signal strength with and without RIS. In the line of sight scenario, the received signal strength, or RSS map, shows that without RIS, the signal strength is already strong around the receiver, but not homogeneous across the room. Adding RIS slightly improves the uniformity of the signal around the receiver, but the gain is limited since the direct path is already strong. The lower signal strength here in the red ellipse corresponds to the RIS position. In the non-line of sight scenario, where an obstacle blocks the direct path between the transmitter and the receiver, the benefits of RIS become clearer. Without RIS, the signal strength drops significantly behind the obstacle. When we introduce the RIS and configure it to reflect the signal toward the receiver, we observe the noticeable improvement in the received signal strength. However, this improvement assumes that the receiver position is known so that the RIS can be configured accordingly. In conclusion, this preliminary study demonstrates that RIS can improve indoor 5G coverage, especially in non-line of sight scenarios. However, the placement of RIS and the accurate knowledge of receiver locations are critical for achieving significant gains. For future work, we plan to extend this study by integrating localization techniques to estimate the position of the transmitter and receiver. This would allow us to implement joint beamforming and potentially track a moving receiver in real time within an indoor environment. That's all I wanted to present today. Thank you for watching this video and for your attention.